Newton's second law of motion. The rate of change of momentum of an object is directly proportional to the balanced force in the direction of the force, which means force is directly proportional to rate of change of momentum. We could also write it that force is directly proportional to rate of change of momentum, means change of momentum over time, or change in momentum over time, that is the rate of change of momentum. Let's consider a body of mass mkg. This body has an initial velocity of say u meter per second, and after some time, say t seconds, the velocity now changes to v meters per second. So now the final velocity will be v meter per second. This happens in time t seconds. Since there is a change in velocity from u meter per second to v meter per second, there will be also a change in momentum. Let P1 be the initial momentum. So we'll say initial momentum P1 will be mass into velocity, that is m into u. And the final momentum, which we will take as P2, will be mass into final velocity, that is mv. Now the change in momentum will be P2 minus P1, because P2 is the final momentum and P1 is the initial momentum. It is mv minus mu. That will be the change in momentum. After finding the change in momentum, let us find the rate of change in momentum. And the rate of change of momentum will be the change in momentum, which is P1 over P2 minus P1 over time. And we substitute the values here, we will put mv is final, mu is initial, over time is the rate of change of momentum. From here we are going to take m common out, and what will remain here is v minus u over t. And we know v minus u over t is acceleration. So this was rate of change of momentum is mv minus mu over t. According to the second law, it's given to us that force is directly proportional to rate of change in momentum, which means force is directly proportional to mv minus mu over t, which is the rate of change in momentum. Now force F, the proportional sign, now this proportional sign here, this proportional sign, I'm going to change it to equal. And when I do that, I have to always introduce a constant. That is the rule of math. So mv minus mu over t. Now this constant, we will just call it as a k. And here we have mv minus mu over t. Now after doing a certain experiments, this k is found out to be 1. So we have F equal to 1 mv minus mu over t. So F equal to, I'll take m common out, what remains is v minus u over t. And now you know that v minus u over t is acceleration. So F equal to m into a. This is how we get the derivation of force. Force equal to mass into acceleration. This is obtained by Newton's second law. Why does a fielder pull his hands backwards with the moving ball? To explain this, let us take There's two pictures. Here in the first picture you have a ball heading right in here, and the player holds it right there. He doesn't pull his hand back, which means if the ball was coming with a velocity of say 12 meter per second, the ball would immediately stop and come to rest. So the V would be 0 meter per second. And that time would be, maybe it would do so in a very short time. Say it would do in 2 seconds. So to go over it again, the ball is heading towards the player with 12 meter per second. It's U, and it stops, so it becomes 0 meter per second, and this happens in a time of say just 2 seconds. So the acceleration in this case, we know what is acceleration, V minus U over T. So the acceleration will be, V was 0 minus 12 over 2, time is 2, so acceleration minus 12 over 2, and that would be minus 6 meter per second square. Why did we get negative? Because the body is slowing down. Now let us calculate the force experienced by the player. So here we have F equal to M into A. Just to make things simple, I'll just imagine the mass of the ball to be 2 kgs. It's too much to be 2 kgs, but we'll just imagine for easy calculations. So mass is 2 and the acceleration we saw is minus 6. So the force experienced by this player is minus 12 newtons. In the second case, again the ball approaches the player with a velocity of 12 meter per second. So U is 12 meter per second. The player now holds the ball, so the final velocity is 0 meter per second. But however here, the ball comes to rest after some time. He lowers his hand, and the time taken to stop the ball is now 4 seconds, more than the earlier case. So the acceleration is V minus U over T. So the acceleration V we know is 0 minus 12 and the T is 4. So acceleration minus 12, and here acceleration will be minus 3 meter per second square. Now let's calculate the force experienced by the player. So we have F equal to M into A, and if you remember, the mass of this ball we have taken as 2 kg. So we have 2, acceleration is minus 3, so the force experienced is minus 6 newtons. Let's compare both the forces. Here the player experiences a force of minus 12, while in this case he experiences a force of minus 6. So in this case he experiences less force. So he does not get hurt. The player's hands don't get hurt. But here he experiences a higher force, because his acceleration was much more. Here the acceleration was minus 6. Here the acceleration was minus 3. So why does a player lower his hand? When he lowers his hand, he decreases the acceleration. Now, and on decreasing the acceleration, the force applied on his hand also decreases. So let me repeat. When he lowers his hand, the stopping time increases. See here, the stopping time was 2 seconds. Here the stopping time was 4 seconds. The stopping time increases. This decreases the acceleration and hence decreases the force. In doing so, he increases the stopping time. This decreases the acceleration. Hence the force experienced by the hands is less. How a karate player breaks a pile of bricks. Now when a karate player breaks a pile of bricks, he hits the bricks, so his hand is up here, he hits the bricks in a very short time. Now because the time is short, the acceleration is large. And since force is mass into acceleration, and since acceleration is large, the force is large. And as the force is large, he is able to break the bricks. So basically, he strikes the bricks here. When he strikes the bricks, he does it very quickly. He takes very less time to do it, does it very, very quickly, and thus increases the acceleration and the force increases. Another application of Newton's second law is when these high jump athletes, have you seen when they jump over sand. And they never jump on a hard flooring, because when they jump on the sand, this increases their stopping time. Like in this case, have you seen the sand sort of compresses, and this increases the stopping time. When stopping time increases, acceleration decreases. And if acceleration decreases, force also decreases. And the athlete does not get hurt. Had the athlete fallen on a cement or a hard flooring, then it would stop immediately. The stopping time would be less. And if stopping time is less, acceleration would be more and the force would be more.